Hello everyone, welcome to the course on basic electronics. The subject code is 23CT23B. Myself Umayas, Assistant Professor Department of ECE. So in this session, we're going to discuss about BJT and FET, that is Module 2. The content of Module 2 is as follows. It consists of Introduction to Transistor Construction, transistor operation, common base configuration, transistors amplifying action, common emitter configuration, common collector configuration, limits of operation, operating point, fixed bias configuration, field effect transistor, introduction, construction and characteristics of JFET, transfer characteristics of depletion type MOSFETs and enhancement type MOSFETs. So here we'll be discussing about DC load line of BJT biasing circuit. So in order to understand the concepts of BJT biasing, transistors used in amplifier circuits must be biased into an on state with constant levels of collector, base and emitter current and constant terminal voltages. The levels of IC and VCE define the transistor DC operating point. The circuit that provides this state is known as a bias circuit. Ideally, the current and voltage levels in bias circuit should remain absolutely constant. In practical circuits, these quantities are affected by the transistor current gain and by temperature changes. The best bias circuits have the greatest stability. They hold the currents and voltages substantially constant regardless of the HFE and variations in temperature. The simple bias circuits are the least costly because they use the smallest number of components, but they are not as stable as more complex circuits. Coming to the DC load line and bias point, the DC load line for a transistor circuit is a straight line. So that is drawn on the transistor output characteristics. For a common emitter circuit, the load line is a graph of collector current versus collector emitter voltage for a given value of collector resistance RC and a given supply voltage VCC. The load line shows all corresponding levels of IC and VCE that can exist in a particular circuit. Consider the common emitter circuit in this figure. Note that the polarities of the transistor terminal voltages, such as that the base emitter junction is forward biased and collector base junction is reverse biased. Collector base junction is reverse biased. So these are the normal bias polarities for the transistor junctions. The DC load line for the circuit in the figure is drawn. So on the device, common emitter characteristics. So the collector emitter voltage is given as VCE is equal to supply voltage minus voltage drop across RC. or VCE is equal to VCC minus ICRC. If the base emitter voltage VBE is 0, the transistor is not conducting and IC is equal to 0. Substituting the VCC and RC values from the figure. So plotting point A on the common emitter characteristics at IC is equal to 0 and VCE will become equal to 20 volts. This is one point on the DC load line. Now assume a collector current of 2 milliamperes and calculate the corresponding collector emitter voltage level. VCE is equal to 20 volts minus of 2 milliamperes into 10k. So this becomes equal to 0. So plotting point B on figure at VCE is equal to 0 and IC is equal to 2 milliamperes. So the straight line drawn through points A and B is the DC load line for RC is equal to 10 kilo ohm and VCC is equal to 20 volts. If either of these two quantities is changed, a new load line must be drawn. As already stated, the DC load line represents all corresponding IC and VCE levels that can exist in the circuit. For example, a point plotted at VCE is equal to 16 volts. VC is equal to 16 volts and IC is equal to 1.5 milliampere. So figure does not appear on the load line. So this combination of voltage and current cannot exist in this particular circuit. Knowing any one of IB, IC or VCE, it is easy to determine the other two from a DC load line drawn on the device characteristics. So it is not always necessary to have the device characteristics in order to draw the DC load line. So the DC bias point or Q point. The DC bias point or quiescent point, also known as the DC operating point, identifies the transistor collector current and collector emitter voltage when there is no input signal at the base terminal. Thus, it defines the DC conditions in the circuit. When a signal is applied to the transistor base, IB varies according to the instantaneous amplitude of the signal. So, this causes IC to vary and consequently produces a variation in VCE. So considering the circuit and the 10 kilo ohm load line drawn for the circuit, assuming that the bias conditions are as identified by the Q point on the load line, when IB is increased from 20 microamperes to 40 microamperes, IC becomes approximately 1.95 milliamperes and VCE becomes zero point 0.5 volts. So at point C on the load line, the VCE change from the Q point. So increasing IB by certain microamperes that causes VCE to decrease by some voltage. So looking at the effect of decreasing the base current when IB is reduced from 20 microamperes to 0, IC goes down approximately to 0.05 milliamperes and VCE goes up to 19.5 volts. So the VCE change is delta VCE is equal to 19.5 minus 10 volts. Decreasing IB by 20 microamperes caused VCE to increase by 9.5 volts. The base current does not have to be varied by the maximum amounts discussed above. The base current does not have to be varied by the maximum amounts, so it can be decreased and increased by smaller amounts. So a base current, for example, if a base current change of plus or minus 10 microamperes would produce a collector current change of plus or minus zero point 0.5 milliamperes and a collector emitter voltage change of plus or minus 5 volts. The maximum possible transistor collector emitter voltage swing for a circuit can be determined without using the transistor characteristics. So it may be assumed that IC can be driven to 0 at one extreme and to VCC by RC at the other extreme. So this changes the collector emitter voltage from VCE is equal to VCC to VCE is equal to 0. So thus with the Q point at the center of the load line, the maximum possible collector voltage swing is seen to be approximately plus or minus VCC by 2. So coming to the selection of Q point, suppose that instead of being biased halfway along the load line, the transistor is biased at IC is equal to zero point 0.5 milliamperes and VCE is equal to VCE to 0. So giving delta VCE is equal to minus 15 volts, reducing IC to 0 increases VCE to VCC, producing delta VCE is equal to plus 5 volts. When used as an amplifier, the transistor output voltage must swing up and down by equal amounts. That is, the output voltage swing must be symmetrical above and below the bias point. So the asymmetrical VCE swing of minus 15 volts and plus 5 volts in figure, it is unsuitable if IC is driven up and down by plus or minus zero point 0.5 milliamperes. Symmetrical output voltage swing of plus or minus 5 volts is obtained. This is the maximum symmetrical output voltage swing that can be achieved with the bias point. In many cases, circuits are designed to have the Q point at the center of the load line to give the largest possible symmetrical output voltage swing. This is especially true for some large signal amplifiers. Small signal amplifiers usually require an output voltage swing not greater than plus or minus 1 volt. So transistors in amplifiers requires an output voltage swing not greater than plus or minus 1 volt. So transistors in amplifiers do not all have to be biased at the center of the DC load line. So coming to the effect of emitter resistor, figure shows a circuit that has a resistor in series with the transistor emitter terminal and the supply voltage connected directly to the collector terminal. In this case, RE is the DC load and equation can be rewritten as VC is equal to VCC minus IE RE. The DC load line is drawn exactly with IE taken as equal to IC for convenience. So in figure B, collector and emitter resistors RC and RE are both present and the total DC load in series with the transistor is RC plus RE. For drawing the DC load line, it is modified to VCE is equal to VCC minus IC into RC plus RE. So coming to the fixed base bias circuit. So the circuit operation and analysis. The transistor bias arrangement is shown in this figure. It is known as base bias and also as fixed current bias. The base current is a constant quantity determined by supply voltage VCC and base resistor RB. Because VCC and RB are constant quantities, IB remains fixed at a particular level, unlike some other bias circuits. Uh, the base current in a base bias circuit is not affected by the transistor current gain. The voltage drop across RB is VCC minus VBE and the base current is IB is equal to VCC minus VBE by RB. In this equation, the base emitter voltage, that is VBE, is taken as 0.7 volts for silicon transistor and zero point 0.3 volts for germanium device. So effect of HFE max and HFE minimum, like when the transistor DC current gain is known, it is quite easy to determine the circuit bias conditions. In practice, the precise current gain of each transistor is normally not known. The transistor is usually identified by its type number, and the maximum and minimum values of current gain can be obtained from the manufacturer's datasheet. In circuit analysis, it is sometimes convenient to use a typical HFE value. So, HFE max and minimum must be used to calculate the range of possible levels of IC and VCE. So this is the problem. Um, the base bias circuit in figure, the circuit diagram is given. RB value is given as 470 kilo ohm. RC value is given as 2.2 kilo ohm. And VCC is equal to 18 volts. VBE is equal to zero point 0.7 volts. And the transistor has HFE is equal to 100. So to determine IB, IC and VCE, so first noting down all the given values. So in order to find IB is equal to VCC minus VBA by RB. So by substituting all the values, we get IB value as 36.8 micro ohms, microamperes, and IC is equal to HFE into IB, that is 3.68 milliamperes. VCE is equal to VCC minus ICRC, that is 9.9 volts. So the effects of HFE max and HFE minimum, which we already discussed, like it is rarely used because of the uncertainty of the Q point. And this is one more problem over that. Well, all the values will be given. So based on the parameters that is to be calculated, we have to calculate it. So for this for the same drawing the load line and point Q pointing for different HFE values can be done. Similarly, for base bias using PNP transistor, the circuit is shown here. Like all of the base bias in BJT circuits discussed so far use NPN transistors. So here is the circuit which shows voltage polarities and current directions are reversed compared to NPN transistor base bias circuits, because it is normal to show the supply voltage with the positive terminal uppermost. So the figure is redrawn here. This is the way that the circuit usually be shown. So these above equations can be applied to analyze the PNP transistor base bias in BJT circuit exactly as for NPN transistor circuits. So these are some of the questions on the base bias circuit. Thank you.